For over 150 years, some paradoxes in classical electrodynamics have remained unsolved. As Feynman said, the problems are associated with the concepts of electromagnetic momentum and energy. New definitions of electromagnetic energy density and momentum flux are the key to solving these paradoxes. It is well known that both fluids have momentum flux when crossing a surface, and so do photons. Therefore, there must be momentum flux for all electromagnetic waves crossing a given surface. An example of the missing electromagnetic momentum flux in Maxwell's equations is the case of a long solenoid with a charged rod in the axis. The magnetic field is in the axis direction, and the electric field is perpendicular to the magnetic field in the radial direction. Both fields are static. A simple calculation shows that the field's momentum is turning in the theta direction according to the Poynting vector, and there has to be a momentum flux flowing in that direction. According to Einstein, any electromagnetic field has mass density. Therefore, the fields should experience centrifugal force, just like the case of fluids and gas with rotational momentum. But we do not see centrifugal forces and momentum flux represented in the motion equations of electromagnetic fields in Minkowski's energy-momentum tensor. In 1911, Minkowski defined electromagnetic energy density as the T00 component and the electromagnetic momentum density as the T0I component. Maxwell stresses Tij are the other components, but there is no independent covariant definition for the electromagnetic momentum and energy density, and we are missing the momentum flux terms that do exist in fluid dynamics. Theoretical physicist Doron Wainfeld proposes a solution in a new theoretical paper. In his paper, Doron suggests that we define a new independent proper covariant tensor for the electromagnetic momentum density, and we define a new electromagnetic energy density proper scalar where F and F special are the known electromagnetic tensor and its dual. With these new definitions, the 4/3 paradox disappears. We can now define the covariant electromagnetic velocity tensor as this. This velocity describes the rate at which electromagnetic momentum is transferred from one point to another inside the volume where the electromagnetic field exists. Using these new definitions, we define a novel proper covariant electromagnetic momentum flux tensor. Combining Minkowski's tensor T and this new momentum flux tensor M gives the new electromagnetic energy momentum tensor. And in tensor form, the Sij are the known Maxwell stresses, and the divergence gives the new extended electromagnetic energy momentum conservation equations that include the momentum flux. In the paper, we prove that the energy momentum conservation equations are equivalent to Maxwell's equation, in conjunction with the divergence of the dual tensor. The four equations of the divergence of the dual tensor are just a mathematical expression stating that the 4 divergence of a 4 vector is null. This equivalence has to hold for the extended electromagnetic energy momentum conservation equation as well. And we can derive the new extended Maxwell's equations. The Lagrangian of the extended Maxwell equations is this. The action is this. The extremum of this action gives the new extended covariant Maxwell's equations in conjunction with the dual tensor equations. By combining the new electromagnetic energy momentum conservation equations with the mechanical conservation equations, we arrive at the combined equations that represent the complete motion equations of charged particles with their fields. It is important to note that the particles and their fields are dynamically coupled and depend on the acceleration as well as distance and velocity. These combined motion equations are non-linear and solve the radiation reaction problem of Abrahams and Lorentz. They also help to explain many newly discovered phenomena of very strong electromagnetic fields. To summarize, we identified that Minkowski's tensor is missing the electromagnetic momentum flux, so we defined a new proper covariant electromagnetic momentum flux tensor and a new extension to the electromagnetic energy momentum conservation equations, as well as a new extension to Maxwell equations to include the momentum flux terms. The new equations present a fundamental change in the understanding of classical electrodynamics that helps to solve many old and new paradoxes where strong electromagnetic fields are present, from the macroscopic size of galaxies to the microscopic sizes of particles.